A thin circular ring of mass m and radius r is rotating about its axis with a constant angular velocity omega. Four objects, each of mass small m, are kept gently to the opposite ends of two perpendicular diameters of the ring. The angular velocity of the ring will be. So we have a question from the chapter System of Particles and Rotational Motion. And in this question, what is mentioned is we have a ring, okay, and I have drawn the diameters here. At the two ends, at the two opposite ends of the perpendicular diameters, we are actually attaching mass as small m. Initially, the ring had an angular velocity omega. We are supposed to find out what is the angular velocity after attaching these masses, right? So here we have to apply the concept of angular momentum conservation. And we know that if there is no external torque acting on the system, then angular momentum will be conserved. So based on angular momentum conservation, we can write I1 omega 1 is equal to I2 omega 2. Okay. So initially, what is the angular momentum? Initially, we just had a ring of mass capital M here. So the moment of inertia of the ring is m r square into omega, which is equal to, we need to know the value of I2, right? I2 will be equal to, we have four masses here, and each of the point mass is at a distance of r from the center. So the moment of inertia of this mass about the central axis will be mr square. For this mass, again mr square, and this mass also mr square, and for this also mr square. So we can write the moment of inertia I2 will be equal to 4 mr square. Okay, substituting here 4 mr square. Now, don't forget that we already have a ring there, right? So I2 will not be just 4 mr square. It will be 4 mr square plus the moment of inertia of the ring. So plus mr square. So there's a plus mr square here. Okay, into omega dash. Right? So r square gets cancelled out from both the sides. So we will have m omega divided by 4m plus capital M, which is equal to our omega dash. So omega dash, the new angular velocity is equal to m omega by 4 into small m plus capital M. Clear? Right. So remember that in questions like this, you have to apply the concept of angular momentum conservation if there is no external torque acting on that system. Okay. So in case you have any doubts, comment below. Okay. Thank you.